That's fantastic. I am not even shouting. So, very well. This is the last class for the dark matter introductory part. And while we wait the customary few minutes for the latecomers, I would like to give you a summary of what we did with Farinaldo during the first 4 classes and give the context. Okay? So on the first day, I presented you the astrophysical evidence, local systems. I didn't even go to cosmology, about the fact that we need, if you want to fix mismatches between different types of observations in galaxies and galaxy clusters, you need a component of matter which is non-luminous. Okay? The name, dark matter, a very well posed name. And I didn't do anything specific about its nature. I didn't postulate anything about its nature, about its distribution. I just said I need something that interacts with gravity and it doesn't interact luminously. Yes. That's why I was asking at the beginning if you can hear me. Can you hear me better now? No? Can you hear me better now? I'm not sure that raising the volume is gonna help. It's more a positioning thing. Can you hear me better now? Now I look like my ears are fluffy. Anyways, doesn't really matter. No, thank you for noticing. So, I was saying, I derived properties of this dark matter, meaning what is it, actually what it is not. Okay, we define it by contrast. And we find out it cannot be very, very things. When I say compact things, I mean things of the size of a planet or a dark planet or a dark star, like the size of the sun. Otherwise, it would cause microlensing. It cannot be self-interacting up to a certain extent. Otherwise, it would not get segregated when the cluster merge. And all these I've done with local probes. Then if I go to cosmological context in the CMB and BBN, CMB alone or CMB with BBN, I find the same thing. And on the top of it, it tells me that it cannot be anything baryonic. It cannot be anything belonging to the standard model. Okay? And on the top of it, I get the cosmological abundance. I get a relic abundance, so a fraction of the critical density that it has to have to fulfill the CMB. Okay? So I learn mostly what it is not. It is not something belonging to the standard model of particle physics. It is something that has to have, at the beginning, a certain relic abundance. And I know that if I put these things, what it is not, consistently in a scenario where there are density perturbations, and these density perturbations are made by the dark matter and some gas, it will collapse into galaxies. Okay? So, and it has to be cold. Okay? Cold means that its velocity at the moment in which, this is the scheme of the classes, that its velocity at the time when it falls into these gravitational potentials, okay, it has to be small. That doesn't mean that mass has to be small, okay? It just means that it has, the T over M has to be small. Now, this is of course all introductory. You can go to a dark matter school that we have here 2 years ago, among many other things, but I'm citing this one. And for each of the things that Farinaldo and I talked about in the last few days, you will find courses. There are classes registered, recorded. You can go there. I can give you more references than the ones I gave you at the beginning. This is just introductory. But the guideline of these classes has been kind of general, to go through the idea of evidence from astrophysical scale, from astrocosmo. And notice there is no need in particle physics for dark matter, meaning that all the evidence and the compelling fact that I want a new particle comes from this, comes from astrophysics. Now, there might be good and motivated scenarios in particle physics in which you get an extra particle for free, but it's not needed. In astrophysics, you need it. Otherwise, the scenario doesn't work. Then we got some properties. Actually, we got some properties complying with what it is not, so non-properties. So it has to comply with the relic abundance. It has to be non-baryonic. It has to be cold worm. Okay? At this point, Farinaldo took these properties and said, okay, I know that these are the generic properties, and I wonder if there is any way that anything I know about quantum field theory and cosmology can give me some candidates that comply with it. If at the best of our knowledge it would have been impossible to extend the standard model or cosmologically to produce something like that, it's game over, right? We are building this scenario, and that would have been an inconsistent scenario. Okay? But as a matter of fact, it turns out that there are classes of models in which you can create extra particles or extend the standard model so as to fulfill these astrophysical requirements. And so one thing that Farinaldo first addressed is the freeze-out, is the thermal production of dark matter. It's not the only possible way to produce the right relic abundance, okay? But it is interesting that if you have a thermal process, the early universe, you can get the right relic abundance. There is also freezing mechanism. Now, I'm not going to go through the details of Farinaldo's class, but there are mechanisms through which you can do it. And then he's asking, okay, this is a general mechanism. Is there any specific extension of the standard model that can comply with this, that can give me this scenario? And as it turns out, there are, okay? So he concentrated on extension of standard model going toward the supersymmetry, so either asymmetric or WIMPs, okay? Weakly interactive massive particle. I would like to stress, we are giving you examples of the most popular models for given reasons. There are other candidates. For instance, there are axions that I'm not going to touch now. Those of you who are particle physicists know a little bit what the axions are, and there are some flavors of the axions that are good dark matter candidate. Now you might say, but the axions are very light. What can I do with it? Well, as long as they are cold, they can provide the structures. It's just that the temperature at which they're produced is much smaller than their mass, or they condensate somehow, but they are cold. So I'm not going to talk about axions, but you're going to hear about it next week, and also how to detect them. But it's just one bright example of the fact that we're not telling you the whole story, because it's obviously impossible in classes, but we are giving you visions of what also you might learn find in the literature in these days. Okay? And today, what I'm going to do is I'm going to give you an example of the question is, okay, I went through the evidence, I went through the properties, I went to the general mechanism of how to produce it. I identified some specific candidates that can do all this. Well, how I can convince myself that these candidates are or are not? How can I actually search and tell, well, the dark matter is this one, or it's not this one, but I want to focus my search now. Okay? So today's class is going to be directed to how to detect this specific class of models. Okay? So it's a very specific, and we went from the very general to the very specific. Okay? And so they are in general called dark matter searches, but I prefer to refer to that as direct and indirect for reasons that you will see. Okay? All right? So you will, Farinaldo has shown you this generic diagram, which doesn't, we didn't really put anything specific into it, but you have a dark matter particle, which I will call chi, okay? Dark matter particle going into a standard model particle, which I will identify as quark right now, but doesn't really matter. okay? And you say, well, if I'm in a WIMP scenario, it means that there is a weak type of interaction, and this weak type of interaction can give me this two-body reaction. I don't know exactly what it is in here. I can write a Lagrangian by time that gives me this interaction, but this generic process is going to take place, okay? And as a matter of fact, Farinaldo has shown that this is nice because that would necessarily dictate a thermal process at some point. So you might have this arrow, and you might also have this arrow of the diagram. So if the energy is high enough, dark matter and dark matter produce standard model particles, and standard model particles produce back dark matter. And this thermal process is the one that dictates the abundance, okay? Now, I'm taking WIMPs in which the mass scale is typically of GeV and above. So this process is typically preferred, because if this is more massive, it's preferred in this direction. But in the early universe, there's a lot of energy, so I can go both sides, okay? And as long as the reactions are kept active, I can go both sides. And I will identify the cross-section for these I will call it the sigma annihilation, okay? There is a cross-section for that. It will depend from the Lagrangian and its parameters, okay? This is clear. If I have a generic Lagrangian, I can go from this, and from the Lagrangian, I can predict sigma annihilation, which will be a function of some of the parameters of the Lagrangian, okay? Sigma annihilation in one direction is not necessarily the same one, but I can find it. Also, if these things is coupled, and there is a weak scale, I might imagine this side of the diagram, right? So basically, dark matter particle scatters over a quark. It's elastic scattering, or mildly inelastic, but it doesn't produce another dark matter particle. It's just the same that bounces back, okay? And this would be a scattering cross-section. And again, this is a phenomenological prescription, and there will be a scattering cross-section that, again, I can predict from the Lagrangian. Okay? It's not the same. This is clear. If I know the Lagrangian, I can predict both of them. Vice versa, if I observe or I know one of them from observations, and I have a specific model in mind, I can go back to the Lagrangian. Or one and the other are related in a specific model because there is a Lagrangian that connects them, right? But I can easily imagine a Lagrangian that predicts a very big one and a very small one. Is this clear? Right? It really depends on your model. But generically, phenomenology is this one, okay? So you will see that this process obviously depends. Well, let's go step by step, all right? So imagine that there is a very simple thing. Dark matter is coupled with a scattering through the quarks. So it obviously cannot be a very big interaction, otherwise I would have seen it. It would violate everything I've seen. But I mentioned, when I say the dark matter is collision length, it's mean below the observed scale. So there is complete freedom at the weak scale for this to happen. I'm not violating my observational constraint. Okay? So I can easily imagine an experiment that says, well, if this cross-section is at the weak scale, then I just imagine an experiment where I put a bunch of material here. So there are atoms with nuclei, with quarks, and what I expect to see in this material, which is under a mountain because I want to shield it, etc., from all the possible contamination of the signal, because what I'm seeing is just a dark matter particle coming here, scattering off and producing some sort of signal. It's detectable, all right? It's something that I can do, and if it's at the weak scale, I can do it, all right? So what I'm looking at is this process. I have dark matter, quark, right? Which is this plot flipped, okay? And this is the principle of direct detection. Then I might think something even better, saying, well, I have a very powerful machine, I raise the energy of this machine, I smash together particles of the standard model, and I produce dark matter. That's what typically you do at a collider, okay? So this thing, this part of the diagram, collider searches, okay? Brilliant. So Eduardo is gonna give a seminar today about like class on this, so I invite you. And then there is something that you might have heard about, and is the fact that if I have this process and I imagine that it can take place in both directions when there is enough energy, namely during the early universe, again, as I can, if I am in an environment where I can give enough energy to the quarks to produce dark matter, if there is enough energy around for the dark matter, I can have only this arrow, right? I can have two dark matter particles going into standard model, correct? And given that, as I said, I am looking specifically at candidates at the GeV scale, typically this reaction is gonna be favored, okay? So if I am somewhere where there is enough dark matter, this process is gonna take place. Right? With a certain cross-section. And this is called, and the point is that I can look at these things. Where is this going to happen? Where there is a lot of dark matter? Anywhere. This process is just gonna happen wherever there is dark matter with a rate that will depend, and we will see it. But typically in space, okay? It's not gonna happen in the Earth. Whereas these I produce in my experiment, in my collider, I have to accelerate these things. So this is an experiment that I can perform. This is an experiment where I have to wait for something to come from the sky, but the experiment is sitting somewhere. Here, I cannot take the dark matter around and smash it together. I just have to wait for this thing to happen somewhere and then look at it. Okay, so typically this will happen with astrophysical observations at high energies, because as I said, this is a GeV scale. Yes. Can maybe.
There are some models that the sun has lots of dark matter.
I'm gonna talk about it in the end, but
okay.
Can you tell me, the blind teaser is, there are not some models where the sun has a lot of dark matter. You have to put the dark matter in the sun, because if it doesn't interact by scattering, if it doesn't interact with the sun by gravitational hour, it ends up in the sun. I'm gonna talk about it if I get time.
You can search for dark matter in colliders. The second method, like produce the dark matter and the dark matter late in standard model particles, and you search for a jet.
In principle, yes, but in practice, you're already very lucky if you manage. But this is another interesting thing. Actually, this is a very good point. When I produce, this is very good point. When I am at a collider, if I'm lucky, I produce something, and this something I will not see. Right? It's typically missing mass. I don't even know if it is dark matter, because as I said, and I forgot to mention, one of the properties of the dark matter, it has to be stable on cosmological timescales. I will very likely produce new physics at the collider, if I am lucky. But it's difficult that, I think it's virtually impossible that by collider alone, I managed to convince myself that it is the dark matter. What I call the dark matter is something that complies with all the astrophysical requirements. Well, first of all, I'm super happy if I already produce new physics, right? So one way to look at it is that if I want to nail the dark matter in a certain model framework, I have to put three things together if I'm thinking of WIMPs. And in fact, the reason why I'm showing all this is that this is a recap of the properties. You will often see these three diagrams that I drew this way. Okay. So if you are looking for some WIMP dark matter, you have to think that these three things play together, because here I'm gonna observe, if you want, it's sigma A this way. No. Sigma A this way, and here I'm going to observe sigma A this way, right? And they are not necessarily the same cross-section. So, as I said, what I have access is these quantities, not the Lagrangian, okay? And I have to reconstruct back the Lagrangian. That's the game I'm trying to play. But first of all, let us see at this point how can even access one of these things. Let's start with direct detection, okay? I build my experiment. I expect to some extent the particles to be WIMPs. What is the rate that I expect in my experiment? This is important to know. I mean, next week, you will learn how the experiments work. But then, what is it that I'm expecting in my detector? I'm expecting a rate of events. This is the event that is going to take place in my detector. Scattering. So, are you all staying at Universe Flat? They give you a lot of food there and coffee, no? Are you awake? Okay, so what's the rate that I expect in a detector? It will depend on the density of particles in the detector, right? It will depend on the density of incoming dark matter. So let's call it like this. I call it Q, and I call it dark matter. No, I call it chi, because that's how I called it. It depends on the cross-section that I'm looking at, okay? Sigma, how did I call it? Scattering. And it will depend on the velocity of the incoming dark matter particle, because there is going to be a flux, right? So if I want, this is, well, actually it does depend, as a matter of fact, of the number density, not on the density, the number of particles, right? So these will depend on the density of the detector divided by the detector, basically the characteristic of the detectors. No? And you will learn about this next week. Okay? This one, the number of incoming dark matter particles, will depend on how much dark matter there is around myself, say around the sun. So the density, what I call the local density of dark matter, divide the mass of the dark matter, multiplied by the velocity of the dark matter, which is actually an integral of the phase-space distribution, because I can not just sensible to the things that are coming here, plus is going to be dependent on the scattering cross-section. So what I will observe is this. I have an experiment. I observe the rate. Now, if I am lucky, I know my experiment very well. And if I am lucky, I know these things. Well, I actually know these things. And therefore, I can reconstruct this. Okay? But since this is the observable, because I'm just taking at the detector and looking what is coming out, if I want to nail down the things that will get me back the Lagrangian, right, I have to know these two things too. And these two things, the density of dark matter around myself and its velocity distribution, I take from astrophysical observations of the dynamics of the galaxy, which is basically what we talked about on the first day. Okay? So if you want, this is the scheme. There is a dark matter cloud around us in the galaxy, right here, and it goes through the Earth. And I want to look at this process of the scattering over the material in the detector. Of course, I'm shielding the detector underneath the mountain. And the thing is that What I have access to is this sort of plots that you will learn a little bit more next week, which means if I'm very good experimentalist, I can neglect all the crap, etc., and I can get to the real rate of events, the very one, if I am a very good experimentalist. But then from the rate of experiment, how do I get to what I want to know, which is the scattering cross-section, which these in turn will tell me what's the intimate nature of dark matter. I have to know these quantities. These two quantities, so this represents the characteristic of the detector. Here is the reduced mass, but not necessarily. This is the two things I want to know. And here, the local dark matter density and the velocity distribution is something that I have to get to the astrophysics. Okay? So, if I want to play the game of direct detection, you have to know the experiments, and these you will learn the next week. Some of them at least. And I need to know the astrophysics around myself. The astro, dark matter, the very local. I think the main organizers are going to kill me for this, but if we have time and if you want, next week I can give you a short class, well, one hour seminar or 45-minute seminar on how you access this quantity. Okay, so the local dark matter density in the Milky Way, that's part of what I'm currently doing. But ask me. You have to ask me, otherwise I'm not going to do it. Okay, you had a question.
The density of the detector, you can relate it to the acceptance of the events.
What I'm calling the density of the detector, it's all the characteristics of the detector, right? You have to know what the material is, how much is going to interact, etc. These are going to talk about the experimentalists. What I want to draw your attention now is that basically there is one part that depends on the detector, and one part is the physics, the particle physics part, which is the scattering cross-section and the mass of the particle, and one part is the astro part. The detector, ideally, I have under control. The astro part is something that you have to know. Hopefully, you have to keep under control from somewhere. And then, if you have everything under control, you can access sigma v and m. So, what is this plot on the right that you are seeing? Can I erase this part of the collider, because I'm not going to talk about it anymore. It's just, this was just to give you an idea. Okay. So typically what you see is this plane here is the mass of the dark matter and the sigma b. So this is a very practical class in which we basically go through what you really see in the literature. What does it mean? It means that, okay, I have a certain observed rate. I know the detector. I assume that I know these two things. And then I expect to put across somewhere here, okay? Now, every signal is going to give me something which is degenerate in sigma e over m, okay? The fact that so far no experiments but Dama, and we can talk about this at the end maybe, has seen anything, it basically means they say, okay, with my detector I have access to a certain region, right? And I have seen nothing. That means that this region is forbidden. It cannot be any particle physics model that predicts something in this region because I should have seen it. Okay? Now, what happens if I have not given myself the right value of this? This line will just move, and actually the rate is directly proportional to it. It's not really true because the dependence on the velocity is not so straightforward, but to good approximation, well, at least it's linear in the dark matter density. Okay, so if I've gotten this wrong, this line will go up or it will go down. Okay. Generally, what experiments do, they give you, say, okay, we adopt this value, we give you the curve for this, and then you can do whatever you want. You can move it if you have a specific idea, a better idea for what the local dark matter density is. That's totally fine, because you can reconvolve the information very easily. Okay, but when you are really searching for the very nature of the dark matter, you have to take into account that there are observational uncertainties on this. Is the principle and the mechanism clear right now? I think for the moment it's everything you need to know to go to the classes and put these experiments in context. Okay, I have a direct detection experiment. What am I doing? Observing the generality between this cross section and the mass. I'm a particle physicist. I want to do the Lagrangian. It's not sure that you can reconstruct the Lagrangian only from that. Okay, but you can start to think. Okay. Now, the second part of the game, which is more interesting, which has created a lot of activity in the last years, the indirect. So this process here, right? And this is the most complicated part, as I will show you, because of the fact that being in space and being astrophysics and non-Galilean science, meaning that I cannot reproduce the experiment, and then I have to make guesses on what I'm seeing, etc. But let's start from the start, which is always a good idea. So, is it clear what I'm trying to do? I'm saying, well, there is dark matter around somewhere in space, and anywhere there is dark matter, this process should take place at a certain rate that I don't know. So it annihilates into something of the standard model. What this something may be really depends on what your Lagrangian is. Does it couple directly to leptons? Does it couple to hadrons? Whatever it is. So this Q actually can be, I don't know, bosons, it can be protons, it can be antiprotons, it can be leptons of some kind, it can be neutrinos, it can be prompt photons. Okay. The interesting thing, so you can choose which channel to use, and actually you can look in different frequencies or different products and then deconvolve the information. But let us say for the moment, I will choose gammas for one reason. First of all, because the gammas, if I produce gammas very close to the source, the gammas will go straight. Okay. Whereas anything else that I produce, if it has an electrical charge, it will be deflected in astrophysics. You can do it, but it's more complicated. So to prove the principle, I'll just take the gammas. And for the secondary reason that whatever I produce, if the environment is rich of gas, this stuff is very high energy, and eventually will produce a secondary gamma in the region where it is produced. So at the end of the day, I am gonna have gammas produced by this annihilation, wherever I am in space. Of course, the characteristic spectrum at emission, so this is the spectrum as emitted around the source, will change depending on the type of secondaries that I have emitted and the mass of the particle of dark matter. But let's say that I'm producing gamma, I know the mass of the particle. And so I'm looking at the gammas. And I'm looking at something around here. So I am here with my eye, and this is the object I'm looking at. Okay? I don't know what this object is for the moment. What is the flux that I expect? Again, this is the rate I expect in the detector if I have direct detection. And now I'm asking myself, what is the rate of the flux that I am expecting? So there will be a rate of production inside the source, okay? Here, which will depend on the number. So this process is a two-body process. I throw two dark matter particles against the other, and I produce something. Okay, so it will depend on the so let's say that this is the rate of annihilations expected. It's proportional to what? The number of projectiles, which is the dark matter particle, the number density of targets, which is the dark matter particle, right? It will also depend on the flux of these particles, right? On their velocity distribution and cross section. So it will depend on sigma annihilation multiplied the velocity. Okay, actually you smear it out, or you integrate it over the velocity, and it will depend on anything else that I've forgotten. No, I think it's more or less everything. This is the rate of events, and then the flux that I'm expecting is obviously going to be this one, this sigma annihilation V multiplied by the energy produced in each collision, which is twice the mass of the dark matter particle. Right? Okay. And this is the rate per unit volume. This is the dark matter particle density. So somehow this is proportional to the dark matter density divided the mass of the dark matter particle. Okay, this is per unit volume, and then if I want, I can just integrate these over the whole source along the line of sight, because what I'm gonna see is whatever is produced from the source along my line of sight in my field view. Okay, so this is to prove that if, and I'm not sure that I managed to observe this flux, but if I observe this flux, this will be dependent on what? On the quantities that I'm interested in, right? Because these are the quantities that will trace me back to the Lagrangian and its parameters. And again, I am depending on something astrophysics, which in this case is not around myself, but it's the density distribution within the target. Okay? Because this process is taking place in the target. On the top of it, all these will produce a certain spectrum, as I said. So the real signal that I expect will also depend, and in this case there is an additional dependence on the Lagrangian, on the branching ratio in some specific channel. As I said, now I'm assuming it's gamma, but if I produce bosons, I'm going to have a certain type of spectrum. If I produce proton and antiprotons, I'm going to have a different type of spectrum. Okay? And of course, I might be producing parts of gammas and part of protons and part of electrons, and I might see the three of them. The point is that obviously, well, I might also be producing neutrinos, and also they also point straight to the source, but their cross-section is much smaller than the gammas. That's why gammas are usually used, okay, because they interact more. The point is that if I'm producing an electron or a proton, actually an electron is in this thing, even if I produce it relatively locally within my galaxy, they will be affected by magnetic fields. So they will not point to the source to a certain extent, right? So the thing that I would like to stress here is that this is the principle. I think it's a good idea to first produce the equation and then show the slides rather than vice versa. So one can. So the idea is that I have this process, and then I can produce a certain different types, and I can observe them in different ways. And this is the flux that I just created. Of course, yes, the flux that I observe at the Earth is divided by the distance, right? It's 1 over the distance square. And actually, if I want to be correct, this distance square should be here. Of course. And again, this is the sketch picture of the fact that gammas and neutrinos point straight to the source, whereas when I produce something which is charged, it's going to be moving around. Okay. And this is the generic equation, and you will find I hate the nomenclature, but you will find that typically this dependence, this integral of the astrophysical quantity of dark matter within the source is referred to as the J factor. Okay? This is nomenclature, you will find it. I don't like it because it flattens the idea. The J factor is not absolute. It will depend on the direction of the target, on the opening. So J factor in the direction of over a certain angle, etc., etc. But just to give you an idea, will depend on a dark matter density square. So if you don't know the dark matter density and you make an assumption, the prediction on your flux is sensitive to the square of your error. Okay? I know that at least one person in this room is wondering why that there is a mistake in this slide, and it's on purpose, right? I'm putting an image in this slide which is misleading, but nobody notices but you. This here and here, right? So there is an uncertainty. I'm gonna get to that later on. No, absolutely not. So how does the indirect dark matter searches work? Because this is the principle, but whereas in direct detection, in the searches through a direct detection channel, it's neat, right? If I can get rid of all the experimental noise, I know that I'm observing a dark matter particle and reconstruct it. Here, that becomes a mess because it's astrophysics. I'm observing from astrophysics. So, recap. Is it clear that the sigma annihilation is not the sigma scattering? But they are related, but they're not the same thing. Okay? Observationally, I'm just observing sigma scattering and sigma annihilation, if I'm able to do it. Then, second thing, let me write down this equation in a cleaner form. Well, you have it up there, but nonetheless. The flux that I expect is proportional to the sigma annihilation V, sometimes averaged over the mass of the particle, sum rho square dV over distance integral, okay? Multiplied by the branching ratio. So now let us say that my goal as an astrophysicist is to maximize the flux that I want to see. Now we're talking about gammas because it's simple. Okay? If I want to maximize that flux, and given the fact that I don't know these ones, but presumably they are a constant, okay? This is the quantity I want to look at, so I cannot change this. Where do I have the choice. This is astrophysics, so I have to choose and look in different directions. Where do I want to look to maximize this flux? So the flux is an expression. This is God-given. I cannot change it. These I have chosen to be the branching ratio into gamma, so also I cannot change. It's God-given. This is distance, and this is rho square. So where do I have to look if I want to maximize this flux? What objects should I choose? Nearby, because it minimizes this, right? Well, it maximizes this. And also very dense, right? Somehow I want to maximize this integral. The compromise between that is around the Earth, it's near, but the volume is small. So the compromise between that is the galactic center. Okay? And I expect the density of dark matter. Remember, this seems counterintuitive because I told you that dark matter doesn't dominate the distribution of matter in the center, which is dominated by the baryons, but the density goes up. So if I'm looking at the galactic center, I'm maximizing this integral of the density. So, okay, this is the galaxy. I'm sitting in the plane somewhere here, and if I look around here, I am choosing a compromise between something very close, relatively close, and where the dark matter is very dense. Very good. So I might maximize this. So I take my flux, and I'm saying, well, I could have been looking somewhere where the flux is like this, but as a matter of fact, now I've just maximized it, and it's over here. And I'm looking at this beautiful flux. So I point my telescope toward the galactic center, and I see a lot of photons. Gamma rays. Have I found the dark matter? No, because unfortunately there's a lot of other stuff that produces gamma rays in the galactic center. So, and typically the flux of this stuff, I made a mistake in this. I overshot. So this is the flux that is predicted by dark matter, okay? Here. And then I observe, I have an observed spectrum which is like this. But first of all, it's much more than the dark matter. So, oh wow, I underestimated my dark matter cross-section of orders of magnitude, and it's not the case. I'm obviously observing a background, or a background. I'm observing astrophysics on which people have spent decades to understand the astrophysics of this. And on the top of it, this is completely masquerading my signal, right? It's a bleeding. So either I have completely under control such knowledge of the signal that if this is at the third digit below, it's 3 orders of magnitude below, I have to have control of the background down to the third digit, or I cannot do it. Or this is astrophysics. This is the flux, but I also have a morphology of the flux, right? I know each point, the dark matter should have sort of spherical, so I might look at the morphology of this signal, okay? On the top of it, if I expect this signal in gammas from here, I do expect a signal in gammas from other places. So I might look in what I do expect from different parts. Now, this class, it's really difficult to keep it contained, but the indirect explodes because it really, how to interpret what you observe is really depends on what you're putting in. But I'm just trying to give you a primer. The other clever thing that I could do is, okay, reducing the distance is absolutely the first thing that comes to my mind, but I might think to go to somewhere which is farther away, but I have no background. That would be a neater part. And in fact, that's what people do. I mentioned that there are small galaxies where the velocity of stars is mostly random, and there is no disk. And those systems, those small galaxies, are usually dark matter dominated. So the mass to luminosity relation is very big. So they are satellites of the Milky Way around. Obviously, this is not in scale, dwarf spheroidal galaxies. And given the fact that they are very old and the gas has been stripped, since typically gamma rays are produced by the fact that there are high energy protons around, cosmic rays, and they hit the gas in the galaxy and they produce a background. And since there is no gas, you have no associated gamma ray background. So when I play the game of indirect detection, I have to cleverly choose my target. And again, right now, I'm only talking about gamma rays. Yes. Yes, but at the moment it's not going to help you. No, with gamma rays probably you can't. I'm not sure. But in any case, at the moment, the dark matter flux is expected is at the gamma ray flux that you would expect from a vanilla WIMP, where you take this number here to be the same one that gives you the relic abundance. So right now, I haven't even talked about what's the natural benchmark for this, okay? But it's clear that in the scenario that Feraldo described, I expect to see something where this is at the order of the GeV and this is at the order of 10 to the minus 26, because this is what gives me. So let's take this thing in mind. I put it here. I expect a flux which at the galactic center is 1 or 2 orders of magnitude below what I see from the galactic center, well, 1-ish, okay? And in dwarf galaxies is really at the sensitivity of the instrument. Now I'm going to come to that. Okay, so telling the polarization would help me if I were already seeing a signal, but I'm not. A signal at the order of what I expect from the dark matter. Yeah, no, sure, right? And there are so many other less complicated things that I can do before going to the polarization. This is giving a primer. I still haven't gotten to where does the sensitivity of the instrument lies, okay? So this game can be complicated in very ways. And now I'm just presenting the principles, otherwise it doesn't make sense to hear about indirect. No, otherwise it doesn't get registered.
So for this model or for this galactic center flux, you're also using a vanilla model for the dark matter density, right?
I'm not using it. I'm just saying what that I expect the density to be higher. I haven't said how much I expect it to be. But in any galactic model, you expect the density of the galactic center to be higher than here. It's just, first of all, you can fit the rotation curve, and second, it's stability. I'm not putting numbers. I'm giving the principle. I can give you a seminar on what you expect to detect. But as I'm saying is, the flux that I expect from the galactic center, I expect it to be higher. Then if I want to make a prediction and I take a specific density profile for the galactic center, my ignorance is squared in the flux. So one has to be extremely careful with that. Okay? But the principle is it depends on the density square and it depends on the 1 over the distance square. Okay? So one other thing that I could do is to go to dwarf galaxies. And there, well, the flux is expected is lower because they're farther away. Okay? The density is slightly higher. And on dwarf galaxies, typically you make smaller mistakes in determining the density than you do at the galactic center. But still, that's the principle. Now, what is it that you're going to see? What is it that you're going to see if you're looking at a real experiment? But first, the question.
On your model, you put the energy of the interaction as the mass of the dark matter, right? But you will not expect like a line on a line on the gamma energy, because the energy is fixed. It's the same mass.
No, basically it's virtually impossible to construct a model which just gives you a line. You might have a line, but that depends on your Lagrangian. So right now, what I was doing when I'm drawing this spectrum. Okay, so this is the spectrum at emission. Okay, this is the energy, and say that I have a certain spectrum. Okay, this spectrum is such it can be that one. In this moment, I'm not choosing any. I'm just telling you there is going to be a spectrum that it respects the property that is equal to the integral of E dn dE dE. Okay? And this is my spectral shape. So, this is the energy of the particle, right? It will annihilate into something, a sum of different spectra, prompt gammas, protons, etc. And of course, I must conserve the energy. And what's the shape? Let's call it spectrum of E. At the moment, I don't know. It will be something. It will have a cutoff at the mass of the particle, because I cannot produce something above. And if I'm looking at the GeV candidate, it will be somewhere around the GeV, below the mass of the particle, under GeV. If I choose 100 GeV. Okay? But so, say that this is what I expect at Earth. So this is E, and this is flux. Okay? And let us say that I'm looking at this galaxy, and I know that I expect in arbitrary units, but there are units, okay? I am expecting this flux of gammas. Okay? And this flux of gammas takes into account the fact that in this moment, I absolutely know the density of the dark matter distribution. I absolutely know the distance of the object, which is also not true. Right? But let's say that I know all this. And let's say that I'm making a choice that all the energy goes in gammas. What do I expect is this flux at Earth. This is the observed flux. Can I observe it or not? Typically, if you look at the sensitivity curves of a gamma experiment or anything else, it's something that goes like this. Right? It means that this is the sensitivity curve of the experiment. Whenever a flux is above this line, I can observe it. Okay? So, if this is the flux that I'm observing, actually, let me draw it with a different color. This is the sensitivity curve of the experiment. If what I'm expecting to see from the dwarf galaxy is above the sensitivity, I should be seeing it. Okay? But this is a spectrum which does not only depend on the target, it's well posed, it will depend on the mass of the dark matter particle, it does depend on sigma v, no? And it does depend on the branching ratio that I'm choosing. Okay? But let us say that I'm fixing all this. I do expect to see this thing. Okay? And I don't see anything. What does it matter? What does it mean? That for this mass of the for this sigma v and for this branching ratio, that's well, as a matter of fact, depends on this. I have to rule out that sigma v, that mass, and that branching ratio because I'm not observing anything. Okay? So basically, if I now go in the plane sigma v and mass, I must say, if this is the flux that I expect from this point, this is ruled out because I'm not seeing it. Okay? So, and you can do this for different predictions for different sigma v and m. So what typically you do is you will see, actually this goes back up, exclusion plots made like this, saying, I have not seen this thing, I have not seen any signal above the sensitivity for those where I expect. But, and therefore they're ruled out. Still, some particles, some natural Lagrangians might live somewhere here in the space. But at the moment, they give me a flux which is below. So I want to build another experiment that has a sensitivity curve that goes lower. Okay? For instance, it's the upgrade from Fermi to CTA, it's different energy, or from Hess to CTA, the energies of the TV. And in principle, you can access this space. Now, you don't see it, your exclusion curves goes down. Obviously, is a very sick way to say, I want to build an experiment so I can go down with my exclusion curve. In principle, you want to see something from this point, right? But what's going on at the moment is that the sensitivity has increased and you can place constraints. Yes, again.
Why does both that exclusion curve and the direct exclusion curve have that shape? Because
Actually, the indirect doesn't have that shape. Well, the direct detection goes very steeply up around a certain mass. It's just because depending on the mass of the detector, you don't have enough energy to bounce the thing. And here, actually, this doesn't go this way. It actually typically goes more like this. Because the signal depends on sigma v over m, so if the mass is smaller and you can still produce that thing, you are maximizing the flux, so you should be seeing it more, so you maximize the exclusion plot. Okay? But thank you for the question, because there was a mistake in those plots. So what you are typically going to see is a constraint of this shape in the mass and sigma v plane. Again, this is the annihilation cross-section, it is not the scattering cross-section. And again, the natural benchmark, if I am believing this scenario which I'm studying, is, well, there is a scale which I'm not drawing, but say that this is the cross-section that I need for producing the relic abundance. There is a natural scale which is this one. So I want to reach this line with all the experiments and for what it is. Okay? Is this clear? Good. I still have 15 minutes. Okay, so this is going very smoothly, I think. Well, and it's at this stage it's extremely complicated to talk about the fact that if I have a specific Lagrangian and I'm expecting photons, well, if I have a specific Lagrangian, I know exactly what the branching ratios in all the particles are. Okay? So I can predict how many photons I would expect from the galactic center. I can predict how many electrons that I do expect from the galactic center. I will not receive electrons from the galactic center because if they are at the 100 GeV, they will synchrotron down, okay? But nonetheless, I can predict in every single channel, given the Lagrangian, what I expect to see. And as it turns out, I can measure leptons around the Earth, and I can make a dark matter searches with that, okay? I don't want to confuse you here, but the idea is that if I have a specific model, I can predict all the observables and go back to that model and constrain it. Okay? I've chosen gammas because they're easier to visualize. But if you go into the indirect dark matter business, you can go to that. Okay? Are there any questions up to now? Because then I want to introduce two things that are a little more edgy. And one, there is a poster about it, which is basically the same principle, but you get rid of the uncertainty. One last thing, let me mention. Say that this is the exclusion plot that I'm getting by looking at a dwarf galaxy, okay? What happens if I've taken this density profile wrong? It means that I'm predicting my flux wrong, and it's either higher or lower. So it means that my predicted flux is either here or here, depending on the sort of mistake that I've done, which is what he was saying about the galactic center. It's the same principle. That means that if I don't see anything, I'm pointing to a wrong sigma v constraint. So this line again goes either up or down. But when you see a constraint, it's typically for a given dark matter distribution in the target. But when you're doing real science, when you really want to put the Lagrangian, reconstruct the Lagrangian, you have to fold in the uncertainties on these astrophysical quantities, okay? They are important. Okay. All right, so let me give you two primers on things that people do again in the literature. So this is, again, this is more like a class for going around the literature and trying to understand what happens in this scenario. So I hope this is clear. And let us stay on the generic formula. And let's say that I have this process again. And let us say that this is my spectrum. Doesn't really matter. Okay? So what I said at the beginning was someone said, oh, where are you looking at? I said, well, where is this taking place? I said in space, right? This process is taking place everywhere. It's just that where the dark matter density is low, this process is suppressed. Okay? Fair enough? So I can if you want, I can integrate this equation all over the visible universe. That's actually what people do. There are extragalactic searches of gamma backgrounds. You integrate it, and of course this huge density field will have dips between galaxies because most of the dark matter. But I can integrate it out. And of course I will not be able to resolve, but it takes place. So those of you who are familiar with cosmology know that the density of matter, rho of m, the cosmological dark matter, is a function of time. So yes, it falls into structure, but imagine that you are in cosmological epochs around PBN, okay? As I said, I am not sensible to dark matter density, but it's there, okay? And it has a cosmological dark density. So this thing goes down because the universe is expanding and actually goes down like the common variable cube, right? So, and in fact, when it's back then, that process is very, not only the universe is very hot, but the dark matter is very dense, okay? So, after these processes stop in both ways, when I produce the dark matter, after it has stopped because I've frozen out, I don't have enough energy to pump this into this, this process will still take in place. It's not a leading process, it's not super important, but it is taking place. If it's taking place in the galaxies, this arrow is also taking place primordially, after the decoupling. It's not important to the energetic of the universe, and it's not important to the energetics of the dark matter. I'm not depleting the density, because this process is subleading, but it's taking place. Okay? I can make the number, and if I take the raw dark matter, which is a certain fraction of the critical density, I can compute the amount of energy that I inject into the surroundings. And this thing is very small. As a matter of fact, if I go around the CMB, this is 5 orders of magnitude below the thermal energy. So it's really non-contributing. But actually what happens is that I can write down this very equation in cosmological terms, right? So I can write down the rate of dark matter annihilations cosmologically, so as a function of the age of the universe, is proportional to what? To the dark matter density square at that cosmological time. If you want, I can see it as redshift. It doesn't really, it's just that the function is inverted. Sigma A B over M multiplied by the mass of the particle. And I know that this function is going up, actually the dark matter density. There is a poster about this, but I wanna give you, so go look at the poster, but I wanna give you the primer. The dark matter density will go as 1 over the redshift cube, because redshift is the inverse of this. So just expect in the early epochs after the combination, these to be more peaked. Now you're saying, well, but this number is very small, so what can I do of it? And on the top of it, I cannot look at photons from redshift 1000. I cannot look at the gammas from redshift 1000, right? But the interesting thing is that, first of all, the energy produced is really subleading, so it's not messing up with the thermal distribution of the CMB, etc. But what happens is that, all right, this is density, this is the arrow time. So here is the thermal production of dark, actually this is the thermal production of dark matter, and then it's evolving cosmologically. You've seen it flat because that was co-moving, but that's like going 1 over cube. And sometime around here, so the dark matter density is frozen right here, and this square thing will produce some energy. Around here, which is CMB production, so Z equal 1000, as you can see, this process is not depleting the density, it's really not affecting it. But around here and around here is still very high. And what happens in terms of stuff is that around here, I can also plot another thing. This is the number of free electrons, okay? What happens at around redshift 1000? The fraction of free electrons is 1, fraction with respect to, it's all ionized. And then, around redshift 1000, this thing goes rapidly down, because it recombines. So, the properties of the CMB, the observed properties of the CMB, do depend on the amount of the floor of electrons. This is 10 to the minus 4. There is a residual fraction, because the photons of the CMB have to go through the gas. Okay? But what happens is that, and so all the properties here are depending on the thermal properties, and here it depends on the slight amount of leftover electrons. Now what happens is that CMB is formed around here, and dark matter is annihilating. And of course, I'm not seeing the gammas, but this small stretch of time is a long time. It's not long cosmologically, but it's a long time. Okay. So what happens is that when I have this process here, chi into whatever, unless it's a neutrino and it streams away, whatever I produce here, it will interact with the gas. It's the same process that produces second order gammas, etc. And it will take a long time. It has a long time to do that. So whatever stuff, say gammas, protons, that is produced in this annihilation, eventually it will get its energy degraded down to the kilo electron volt and then electron volt. So what dark matter is doing is decoupled, is not dictating the evolution of the universe, is not changing the dark matter density, but there is a matter of fact, dark matter annihilation is producing some ionizations in the gas, because it's a little bit of energy. So it's altering the floor. And this in turns, it's changing the spectrum of the CMB. So that's a way, also a way to look at the effects of dark matter annihilation. The very neat thing, the very important thing, is that it depends on the dark matter density. But at that point, there are no structures, right? It's cosmological. And therefore, I exactly know the density. It's the cosmological smooth density. So whatever this observable is not dependent from the uncertainties that I introduced before. Okay? So remember that together with the galactic center, together with the dwarf galaxies, CMB is a probe of, can be a probe of the dark matter annihilation within this. One last thing before I go, 4 or 5 minutes. Someone mentioned that in some models, dark matter should be in the sun. So, and I touch this because it connects to the other part of the talk. So we have the sun. The sun is around here. And dark matter is going through the sun. Free flowing through the sun. What happens to the dark matter when it goes through the sun? It gets mildly deflected, no? But it doesn't go into the sun. There is a gravitational focus, but if it's collisionless, it doesn't lose energy, it doesn't end up in the sun, right? On the other hand, if there is a weak scattering with the sun, with anything making the sun, so this process here, and if I'm looking at a particle of 100 GeV, what happens? It scatters, some of them will scatter in the sun, is exactly the same process that takes place in your detector. And if they're something of 100 GeV, they are heavier than the protons, which make up 95% of the sun. And therefore, since they are heavier, kinematics, they will give energy to the proton. But if they give energy to the proton, what do? They lose energy. So their orbit becomes tighter. Okay? You can integrate over the process, but what is important is that this process will depend on the scattering cross-section, right? And you can integrate over this process, and you can find that some dark matter will actually accumulate inside the sun. Okay? But at this point, if I am in this self-consistent scenario, and if I have an enhanced dark matter density in the sun, it can also annihilate, right? So I will have a dark matter density inside the sun that is actually a function of the scattering cross-section. And then I apply the flux of whatever I produce, and this thing will annihilate with sigma E. So I am putting stuff in the sun by virtue of the scattering cross-section, and it's annihilating by virtue of the annihilation cross-section. Okay? And the sun has an optical depth which is very high. So if I produce gammas, what happens to the gammas? They get stuck in the sun. You have a lot of material on the top of it. If you get protons, whatever, it gets stuck in the sun. The only thing that is able to stream out of the sun is neutrinos. So not only you have neutrinos from somewhere from prompt annihilation, but you might have 100-ish GeV neutrinos, because that's a spectrum coming from the center of the sun. So neutrinos are an indirect probe, but you can find out that actually you can integrate this out. They will probe the scattering cross-section, not the annihilation cross-section. Okay? So when people say, I have these ice cube constraints, you might have two types of ice cube constraints or neutrino constraints. One is from the prompt annihilation somewhere, but they're typically not competitive, because of course, if you're annihilating into neutrinos and gammas from somewhere, you're going to see more gammas, so the constraints are more. But in the sun, there's only neutrinos. But those are depending on the scattering cross-section. Okay? So let me wrap up, because I'm done. My time is up, right? And so you have direct detection, that is the scattering of something in your detector, and you will go through the experiments next week. And one thing, remember that, okay, you perform the experiment, you get a limit on the sigma, but that limit will depend on your assumption on the local dark matter density. So if you want to understand the underlying particle physics, or even the phenomenological cross-section, you will need to know at least this information. But then there is no choice of experiment. The experiment is sitting in the Earth. You might have different materials because they're sensitive to different masses, etc. You will hear this next week. Concerning indirect detection, it's a very complicated game, because you have to choose the target object. Galactic center, dwarf galaxies, whatever is best. Where you have less background, but you're maximizing your choice. You have to choose the observable, and actually the target might depend on the observable. So you're looking at gammas, you're looking at charged leptons, you're looking at proton antiprotons. Okay? And then you can interplay these things together. And that's a very complicated game. And in principle, you can also, well, I'm not saying the target objects can be also the CMB. And there is a faint chance for neutrinos as well. Again, this class is non-conclusive in the sense that I cannot give you a wrap-up on what indirect detection is finding. You were seeing some exclusion plots from Farinaldo, and the punchline is that the sensitivity of gamma rays or other experiments today is reaching the point of this sigma thermal cross-section, which is the benchmark point in the relic production. That's the reason why we thought about these sort of models in the first place. But it's not necessarily the whole game. Okay? And I hope this is not confusing you, but I hope now you have a grasp on what are the principles of direct and indirect, and you can go more. There are classes of Nassim Bozornia on direct detection, on the phenomenology of direct detection in the school, and from Francesca Calore on indirect. And I'm here, and if you ask me next week, I can give you a seminar class on the how to determine this quantity or the quantity of dark matter inside your target, whatever the target is, because that's also extremely important. Okay? Questions?
Well, actually, you don't have time for questions, but let's take like 2 questions. And of course, please write down your questions, and we'll have the discussion session in the afternoon, and Fabio will be there to answer lots of questions. So there's one in the very back there.
Can I mention something before the question? Yes. There is a common mistake in the community. I am not observing anything in direct detection or in indirect, therefore dark matter paradigm is wrong. Is it clear from everything we said this week, and I wrapped up at the beginning, that direct, indirect, or even specific searches through actions are looking at specific candidates that we all agree are not necessarily the ones? The evidence from dark matter comes from Astro and Cosmo. Not finding anything, it might rule out entirely what you thought dark matter was. It might rule out entirely your supersymmetric scenario, whatever. It might destroy the life of theorists. But I'm not a theorist. But it doesn't change the scenario that we describe. It doesn't touch the solidity of that scenario, okay?
Another question?
Another question? Oh, come on.
Okay. I'm sure you have lots of questions for the afternoon session, so we can go to the coffee break and we'll be back in 25-ish minutes.